Okay, so let's have a look at a more practical use of the second derivative. Let's think about things that we know. So we know that for the function f of x, f dash of x is the gradient of the function, okay? That gives us the slope of the curve at any point. If the derivative is equal to 0, well, we know that they're stationary points. Those stationary points could be a maximum, minimum, or our stationary point of inflection, typically our x cubed sort of graph. All right, if the second derivative is equal to 0, all right, this gives us a point of inflection of the curve. Now, this could be a stationary point of inflection or an ordinary point of inflection. So I guess what we're thinking about is the second derivative equals 0 means the gradient is at its maximum or minimum. So our non-stationary point of inflection, if we think about our cubic graph, we're going up, okay, we come down, it's getting steep, and then at some point in time it starts to turn around to head back up again. So it's that point there is my point of inflection, where the gradient is as steep as it's going to be, and then it starts to get flat again. All right, and at that point there, the second derivative is equal to 0. All right, so obviously also equal to 0 at that point there. All right. Okay, so let's have a look at a couple of examples just working through. All right, by considering the graphs of f dash of x and f double dash of x, identify all the key points. Okay, so instead of going through the process of differentiating what is a pretty straightforward function, let's just have a look at our derivative graph. So there's f dash of x, and here's f double dash of x. Okay, so what is it telling me? It's telling me here, let's consider f double dashed. So the second derivative is equal to 0 at x equal to 0 and 2. So that makes some points of inflection. Okay, if we consider in turn, I probably should color code it, f dashed of x is equal to 0 at 0 and what's that? 3 looks like. So those 2 points are stationary points. Now we know f double dashed of x is equal to f dash of x equal to 0. So that makes x equal to 0 a stationary point of inflection. Okay, and at x equal to 3, at x equal to 2, this point here, just a normal point of inflection. All right. So in terms of a graph, we know we're a quartic graph. So even if we just factorise that with an x cubed and a 4 minus x, well, we're probably going to have an intercept out here at 4. Okay. As it turns out, a point of inflection there, it's a negative cubic, so it's going to look something like this. Cubic graph, it's going to continue to increase until we get to 2. Then it's going to start to flatten out a bit, turning point at 3, and then come back down again. Yeah, so there's my turning point. There's my normal point of inflection. There's my stationary point of inflection. And in fact, if I add the actual graph, you can see that that's pretty much what we get, isn't it? So the y value is obviously a bit harder to ascertain without doing calculations, but the key points, turning point at 3, point of inflection at 2, where it matches off with the second derivative, point of inflection, okay, a stationary point of inflection where each of the functions, f dash x, f double dash of x is equal to 0, derivative is, what's the green one? Green one is the second derivative. Second derivative is 0 at 2, so there's my point of inflection. Okay, so it kind of matches off. So in here we actually need to find the intercepts, any turning point. So we actually have to go through the calculations. So obviously x-intercepts, y is equal to 0. So I'm going to have negative x squared minus 9 is equal to 0. Therefore, we get x equal to 0, x equals plus or minus 3. Repeated factor at x equal to 0, so we know that that's going to be a turning point. So I've got minus 3, 3, 0. Let's work out, probably change the colour up. Let's go for dy dx. So if we actually work out the function, it's probably easier. Negative x to the 4 minus plus 9x squared. So dy dx is going to be negative 4x cubed plus 18x. So we'll take out maybe a negative 2x out the front. Gives me x squared minus 9. Let's just pick up that little 2 in there, 2x squared. I was wondering why I was going to get 3 again. So again, I get stationary points at x equal to 0 or x equal plus or minus square root of 9 on 2, which is square root 3 on root 2. So there's my turning points. So we've got a negative quartic graph. Let's just keep working through. And I've got the second derivative, dx squared x squared y dx squared is equal to negative 12x squared plus 18. So negative 12x squared equals negative 18. X squared is equal to 6. What's that? 3 on 2. So x equals plus or minus the square root of 3 on 2. So there's my points of inflection. Okay. Now, notice that where the second derivative is 0, the first derivative isn't 0, so there's no stationary points of inflection. So if I want to sketch this graph from my knowledge of even before we sort of looked at our derivatives, second derivatives, we know it's looking a bit like this. Okay, repeated factor at the origin, so it's a turning point. Single factors at negative 3 and 3, so it's points of intersection. Whereabouts is the derivative equal to 0? At negative 3 on root 2 something, positive 3 on root 2 something. My points of inflection are those 2 points there, which is plus or minus, what is it? Plus or minus the square root of 3 over 2. Should just fix that up a bit better. Hence, guess to find where the curve is at its steepest. So, curve at steepest at x equals plus or minus root 3 on 2. Okay. I guess positive gradient. So steepest, blah, blah, find the intercepts with the axis, any turning points and point of inflection. Okay. So look, I've been a bit lazy. I didn't find my y values, but I'm sure you can work that out. So things to note. What is it? Things to note. There is no common point where the first and second derivatives equal 0, so it's safe to assume no stationary point of inflection, and that's what we found. Points of inflection are where the gradient is at its maximum or minimum. Therefore, the point where the curve is steepest is at either 3 on root 6 or negative 3 on root 6. Okay, so steepness just refers to the gradient, not the sign of the gradient. I guess the next part of this then we sort of leads us into talking about concavity, okay, where a function is concave up or concave down. And if you like concave up graphs, it's the curving nature of the graph, and we'll see that on the next slide. Yeah, the curving nature is curving up or it's curving down. So in here, my graph is curving down to there, and then if you like in green, it's curving up all the way through here, and then curving down again through here. So you can see where that concavity changes sign where we go from concave up to concave down. That's my point of inflection. Okay, and that's sort of what we talk about here. The point of inflection occurs where a sign of the second derivative changes, where the curve changes from concave up to concave down, or vice versa. Okay. Now, at the point of inflection, the tangent will pass through the curve. Okay, it's sort of just neither here nor there. There is a point of inflection on the graph of y equals f of x equals a, where both f dash and f double dash exist. Then we must have f double dash of a equal to 0, but the converse doesn't hold. In other words, if there is a point of inflection, okay, and the derivatives exist, then the second derivative must be 0. But just because the second derivative is equal to 0, it doesn't mean that we have a point of inflection. And I guess straight away the really simple example is something like, probably the wrong pen, x to the 4. Yeah? Differentiate, differentiate, differentiate. The derivatives are all 0 at 0. But clearly, at x equal to 0, it's not a point of inflection. It's just a station. It's just a turning point minimum. All right. So just because the second derivative is 0 doesn't make it a point of inflection. We have to check the first derivative at that point as well. And read it. If the second derivative is greater than 0, it's concave up. All right. So for each of the following functions, find the coordinates of the points of inflection of the curve and state the intervals where the graph is concave up. All right, so let's just check our definitions again. So in other words, that's just saying find f double dashed of x to be greater than 0. So f dashed of x is equal to 3x squared, f double dashed of x is equal to 6x. F double dashed of x is greater than 0 if x is greater than 0. So that kind of makes sense. So if I was just do a quick sketch of that one, what's the graph x cubed? And we want to know where the graph is concave up. It says where x is greater than 0, and that seems to match off pretty well. All right. Negative x cubed is not going to be massively different, is it? Let's go straight to f double dashed of x will be equal to negative 6x. Therefore, x is less than 0. And my negative cubic, I might just go up on the same graph. And again, it's that section there, isn't it? So we probably should formally state concave up for x less than 0. So f dashed of x is equal to 3x squared minus 6x. F double dashed of x is equal to 6x minus 6 is greater than 0 for x is greater than 1. Okay. What's our derivatives here? Let's have a look. So f dashed of x is equal to, quotient rule, derivative of the top, 0, that's right, minus the derivative of the bottom over the bottom squared. Okay, so f double dashed of x is given by the derivative of the top, which is negative 2 times the bottom, x squared minus 4 all squared, subtract the derivative of the bottom, which if we just have a look over here, gives me 4x outside of x squared minus 4. That should be to the 1, not to the 3. Don't know what happened there. Times the top all over the bottom squared. So what does that give me? That gives me, if I take x squared minus 4 out the front as a common factor, I get negative 2 times x squared minus 4, x squared minus 4, minus a minus is a plus 8x squared all over x squared minus 4 to the 4. So what does that mean? They cancel out to leave me with negative 2x squared plus 8x squared is 6x squared plus 8 all over x squared minus 4 cubed. So finally, this numerator is greater than 0 always, isn't it? Because it's x squared and we're just adding numbers in that. So we need x squared minus 4 all cubed to be greater than 0, which means x squared minus 4 has to be greater than 0. X squared has got to be greater than 4. So the magnitude of x has got to be greater than 2. So that means that x is going to be less than negative 2 or x is greater than 2. And that will give me my second derivative as being greater than 0. Messy. Probably all the differentiation stuff is not really a tech-free, to be honest, but it's still good practice. All right, let's have a look at this next function. No idea what it looks like, but I guess that's what we're sort of looking to do, aren't we? So f dash of x is equal to, what's the derivative of 1 on x? X to the minus 1, isn't it? So it's minus 1 on x squared times 6 minus derivative of log x is 1 on x. So therefore we get f dash of x is equal to negative 6 on x squared plus, that should be, right thing in there, plus 3 on x. Okay, so then let's have a look at f double dash of x is equal to, let's just write it as 6x to the minus 2 plus 3x to the minus 1. So what's that derivative going to give me? It's going to give me 12x. Let's just write it as 12 on x cubed minus 3 on x squared. All right, so what do we know? Let's go f dash of x equal to 0. So we're going to have, well, let's just take, what if we just take negative 1 on x squared at the front, and that gives me 6 minus 3x, yeah, for the derivative. Therefore, x equal to a half is a stationary point of some kind. Okay, what about the second? And I should say, oh, well, x is asymptotic at x equal to 0. F double dashed of x, let's factorise that with a 1 on x cubed out the actually we'll take 3 on x cubed out the front, and that's going to give me with a 4 minus x. That seem about right. 12 on x cubed minus 3x on x squared looks about right. Therefore, at x equal to 4, we have a point of inflection. Any x-intercepts? We can try and work with some addition of ordinates, couldn't we? What do we know? What do we know? Well, the natural log function is undefined, so the domain is going to be x is greater than 0. So let's straight away, let's just change this fraction. Let's just work this section here. Okay, we do know that there is an asymptote at x equal to 0. I do know that, well, let's go have a look at x equal to 4 is a point of inflection. And what was the other one? At x equal to a half. okay, is a stationary point. All right, let's have a look at this graph here. So for f double dashed of x greater than 0, when is it going to be greater than 0? Well, if x is less than 4, don't forget x is positive, so 3 on x cubed will always be positive. So we are concave up until 4, and then concave down after 4. All right, let's look at this x equal to a half. If x is equal to a half, just work out where this stationary point is. If x is equal to a half, f of a half is going to be equal to what? 6 on x, which is 12 minus 6 plus 3 natural log of a half. Excuse me. So we know that 12 minus 6 is 6. Now, natural log of a half is in fact negative, isn't it? So it's minus 3 natural log 2. So, which on our CAS gives us about negative 0.23. So we know that my turning point's going to be there and it's going to be a minimum because my graph is concave up through to there. And then after there, it's concave down. And we can sort of infer the rest of the graph really from our knowledge of our ordinates. So because it's concave up, the graph has to increase through here as x gets close to 0. 6 on x is obviously really big. Natural log of x gets down to be a big negative. Which one's bigger? Well, obviously, as it turns out, the 6 on x must be bigger. If x gets really big, 6 on x is basically 0. So we end up with a graph that looks a bit like the log function, which is really what this section of the graph here starts to look like. The log function as we get bigger. Notice it's concave down. Through the middle here, all the way through here, it's concave up, down to a minimum. And we would need technology, and even the location of that minimum, to be honest. Natural log of 2, how big is it? Off the top of my head, I'm not too sure. So that's, I guess, all the key features. A half, why is it there? Why is there a minimum there? Why is there a point of inflection there? So we can use that information to help find all those things. And then we can tie that in a little bit with a second derivative test for local maximum and minimum. Okay, so just extending what we're looking through, if my second derivative is less than 0, it's concave down, isn't it? So that must be a maximum in that area. And if my second derivative is greater than 0, it's concave up, which means there must be a minimum in that area. All right, so you can use that in methods as well, to be honest. One more question. Big section, this one. Consider the function with the rule. Find g dash of x, f dash of x. Okay. G dash of x is equal to, using a u substitution, is e to the u, so it's going to be 2x times e to the x squared. G double dashed of x is equal to the derivative of the first times the second plus the derivative of the second, which we just worked out, times the first. So let's simplify a fraction. I reckon we can take a 2e to the x squared out the front and get 1 plus 2x squared. Does that look right? Okay, so we can see there the three functions defined between -1 and 1. So the code there should tell you which one's which. All right, so solve the equation g dash of x equal to 0. So obviously that implies, so let's call that d. We need 0 is equal to 2xe to the x squared. So null factor law, 0 is equal to 2x or e to the x squared is equal to 0. So there's no solutions for that. Therefore, at x equal to 0 is the only place where g dash of x is equal to 0, which is our minimum there on the axis. E, show that g dash of x, double dash of x is greater than 0 for all x. So we've got 2e to the x squared outside of 1 plus 2x squared. Now, since e to the x squared is greater than 0, now that's for all x, okay, and x squared is greater than, well, must be greater than or equal to 0, so it should be greater than or equal to 0. It's also greater than 0 for all x. Therefore, the product of those two terms is also greater than or equal to 0 for all x. Righto, so state the intervals for which g dash of x is greater than 0 and g dash of x, is less than 0. Well, that's easy enough. So, again, so what are we calling that one? F, e to the x squared is in reality e to the power of some number where k is greater than or equal to 0. So that sort of explains why e to the x squared is always positive or 0. In fact, it's greater than 0, isn't it? Because e to the 0 is 1, and then it just approaches the axis. And in fact, I tell a lie, it goes the other way, doesn't it? All the values are going to get bigger. Which means then, what do we want to do? For g dash of x to be less than 0, we need the other term. We need 2x to be less than 0. Therefore, x is less than 0. For g dash of x to be greater than 0, we need x to be greater than 0. And that, look, you can see that graphically, can't you? If you come up on the graph, the red line is my original function. So the gradient of the function is positive through there, which is what the blue line tells us. Yeah, the gradient is greater than 0. The derivative here is less than 0, which corresponds to the green section of that derivative. And in here, the green line is my second derivative, and it's greater than 0 the whole time, which suggests to me then that the function is concave up the whole time, which is what we get there from the other graph. All right. Slowly but surely we're getting there. So consider the graph of y equals f of x, where f of x is that. Find the coordinates of the stationary points and determine their nature using the second derivative test. Okay, so let's write f of x equals 10x squared minus x cubed. F dashed of x is equal to 20x minus 3x squared. Solve that equal to 0. Turning points, I'm going to take x out the front. 20 minus 3x equal to 0. Therefore we get x equal to 0. And what's we going to, x is equal to 20 over 3. So at x equal to 0, y is equal to 0. And at x equal to 20 on 3, what's y equal to? Let's work out f of 20 on 3 is equal to x squared, 400 on 9 times 10, we'll call that 90, minus, tell a lie, let's go back, not 90 on 9, so we're going to substitute 20 on 3 in, so let's call it 30 on 3 minus 20 on 3, which gives me 10 on 3 in the brackets, so we're going to have 4,000 on 3 nines are 27. That'll do. So there's my stationary point. 1,000 on 27. I don't know if it would simplify, to be honest. Okay, determine their nature. So their nature, f double dashed of x is equal to 20 minus 6x. So at x equal to 0, f double dashed of x is greater than 0. Therefore, 0, 0 is a minimum because it's concave up. And f double dashed of 20 on 3 is equal to 20 minus 120 on 3, which is 20 minus 40, which is less than 0. Therefore, the point 20 on 3 for 1000 on 27 is concave down, so it's a maximum. Local maximum, to be more precise. Find coordinates of the points of inflection and find the gradient of this point. So we'll call B, we'll go to yellow. So points of inflection, we need f double dashed of x equal to 0. Therefore we get 20 minus 6x. So 20 on 6 is equal to x. Coordinate, so that's going to be the point 10 on 3. Substitute that in. What's that going to be? That's going to be 100 on 9 minus 30 on 3 minus 10 on 3, which is 20 on 3, which is 2000 on 27. So there's my point of inflection at 10 on 3, f dashed of 10 on 3 is equal to, what's it going to be? It's going to be 200 on 3 minus, what's that? 100 on 9 times 3, 300 on 9. So 600 minus 300, which is going to be positive 309. So that's what the gradient is. Gradient is equal to, what's that about? 27 is 3 times, isn't it? So it's about 33.333. On the one set of axes, sketch the graphs of blah, 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 between 0 and 10. Right. Can I cheat and just give you the graph? I'm going to cheat, and I'm just going to give you the calculator version. Okay, and there's our graphs there magically appear. But really, there's nothing there that we don't know, especially the original graph. The original graph, you looked at the top of your screen, negative cubic, turning point at x squared because it's a repeated factor, it comes back down through 10. And then everything sort of follows from there a little bit, doesn't it? All right, hope we're getting a feel for that. Using a CAS calculator, find the stationary points and the points of inflection of the graph of e to the x sine x. So let's just do exactly what I've just done, is put those values into a CAS. And voila. Now we have all the key values that we need. We might just need to make it a bit bigger. Whoop, undo that. Make it a smidgen bigger. So use the CAS, find the stationary points and the points of inflection. So stationary points are going to occur where the derivative is 0. So that's where the derivative is there. So that means I'm going to have the points, stationary points, 3 pi on 4. If I substitute 3 pi on 4 in, I get comma root 2 on 2e to the 3 pi on 4, and my other stationary point is at 7 pi on 4. You can just barely make out. It's going to be at root 2 on 2e to the 7 pi on 4. Points and the points of inflection. The points of inflection are where the second derivative is 0, which is here. So inflection, so it's just a pi on 2 e to the pi on 2 and 3 pi on 2 e to the 3 pi on 2. Obviously because sine at those points is 1 and -1, so -1, so it's the negative sign there, which is a bit hard to see. All right, well hopefully that's got you somewhere to go, boys, and yeah, get to it.